The next talk is on monotone policy bugs from bugs and additively homomorphic encryption, and Shafiq will give the talk.
Thank you for the intro. Okay, so my name is Shafiq. Today I'm going to talk to you about monotone bugs from bugs and additively homomorphic encryption. This is a joint work with my advisors, Brent Waters and David Will. So let's start by quickly recalling what a bug is. In non-interactive batch arguments, in this setting we have a prover that wants to convince a verifier that k NP statements are correct statements. Okay? We have like the normal requirements of a proof system. So we have completeness, saying that if all of the statements are true and the honest prover indeed holds the correct witnesses, then it should be able to convince the verifier. On the other hand, if at least one of these statements is not true, then the verifier should reject. And to make this thing non-trivial, we have a succinctness requirement which states that the proof length should be sublinear in the number of statements, which we will denote by k throughout the talk. And usually we want it to be even polylogarithmic. Throughout this talk, we're going to talk about polylogarithmic proof length. So this is the basic definition of a barg, but all of the constructions satisfy a stronger security property, which is called somewhere extractability. So a somewhere extractable barg offers an alternative CRS generation algorithm called trapgen, which takes as an input an index I and outputs a CRS alongside a secret trapdoor. And the first requirement that we have is that this CRS that we can generate using trapgen is computationally indistinguishable from the honest CRS. The second requirement is the extraction requirement. It says that if the CRS is generated to be binding on an index I and the verifier accepts the proof, then we should be able to extract, using the trapdoor, a witness for instance I. And of course, it's an accepting witness. So that's somewhere extractable bargs. Now here, I want to convince you that bargs are important, but probably know that they are. So by definition, they allow us to amortize the cost of proving many NP statements, but they have many other applications. For example, they can be used to get snogs for P or RAM delegation. They can be used to get NISICs. They can be used for aggregate signatures, and I'm probably missing many other applications, but there's just a few to show an example. And because they're very useful, we as a community have spent a lot of time and effort to try and construct them from a wide variety of assumptions. So now we have constructions based on LWE, on pairings, on sub-exponential DDH. So yeah, bargs, important. And I want to talk specifically about one of the applications right now. So let's take a little quick detour, which will help me introduce what I want to introduce later, which is aggregate signatures. So specifically, I will talk about a more restricted setting, multi-signatures. So here we have k parties, and we want to prove that all of them have signed a certain message M. So in this case, I'm the aggregator. I have their verification keys, of course, because they're public. They send me their signatures on this specific message M, and I want to convince someone, a verifier, that they indeed have signed those messages. So I aggregate them, and I send the aggregate signature to the verifier. And again, to make the thing non-trivial, we require that the aggregate signature is succinct. So the length should be, again, polylogarithmic in the number of players k. All right, so we can imagine that in some settings, we don't have to convince someone that all of the players have signed the message. Maybe it's enough to just prove that the number of signers is above a certain threshold. So this is threshold multi-signatures. And here again, we aggregate them, and we want to convince the verifier that maybe most of the players have signed the message. And we have the same succinctness property, and we can generalize it even more to any monotone policy. For example, weighted thresholds, or I guess that's the most natural one, so let's just talk about weighted thresholds. But you can think of other monotone policies. Just as a reminder, monotone Boolean circuit is a Boolean circuit without negation, so it only has and OR gates. And this kind of circuit computes a monotone policy. And the class of monotone policies that you can compute here is very rich. It captures conjunction, disjunction, majority, weighted thresholds, monotone CNF. Now, because we can construct aggregate signatures from bargs, then maybe we can construct also monotone multi-signatures from something that we can call monotone bargs. And indeed, Brakersky et al. And Crypto23 introduced the notion of monotone policy barg. So it's very similar to a barg, but now in addition, we have as input a monotone policy over k bits. And we modify the completeness and soundness properties as you would expect. So first of all, we define a bit, like an indicator bit, bi, for every one of the instances, which just indicates whether the instance is in the language or not. And now we modify the completeness property to say that the verifier should accept if the bits satisfy the policy. Again, if you think of a threshold, then it should accept if most of these statements are true. On the other hand, we modify soundness so that the verifier must reject if the bits do not satisfy the policy. And we have the same succinctness property. Sorry? Great question. I should have defined it. So n is the length of each one of the instances. Thanks for asking. All right, so what do we know about monotone policy bargs? So first of all, snarks trivially imply bargs and monotone policy bargs, okay? But of course, snarks require either heavy machinery or idealized models or falsifiable assumptions, all that stuff. So we're interested in assumptions that do not imply snarks. On the other hand, monotone policy bargs are a generalization of bargs, right? In the case of, what's the word, conjunction. Right. So it's very natural to start from barg as a baseline assumption and ask what else do we need in order to compile it into a monotone policy barg. So the previous work of Brakersky et al. Showed that a regular barg alongside a fully homomorphic encryption can be used to give us a monotone policy barg for all polynomial-sized monotone circuits. In addition, if we restrict ourselves to like more constrained monotone circuits, then it's enough to assume collision-resistant hash instead of fully homomorphic encryption, and we get bargs for those constrained monotone monotone circuits, for example, for log depth or read once bounded space. But in this work, we're interested in the general case, so let's ignore the second line for a bit. And this is basically the only construction that we have. It must use fully homomorphic encryption. So in this work, we ask, is fully homomorphic encryption really necessary? Or more generally, what assumptions do we need in order to compile bargs into monotone policy bargs? So our result basically states that it's enough to assume additively homomorphic encryption. So we can compile any barg into a general monotone policy barg using additively homomorphic encryption. And the formal theorem statement is that we have to assume additively homomorphic encryption at a somewhere extractable barg, which is why I defined the somewhere extractability before. And using those two ingredients, we can get a monotone policy barg for all polynomial-sized monotone circuits with the proof size that you want and non-adaptive soundness. Now, as a corollary, basically we can now instantiate monotone policy bargs from all of the assumptions that I mentioned before that actually give us bargs. So now we can get them from bilinear maps and sub-exponential DDH. All right, now let's go back to signatures for a little bit. So actually, if we take batch arguments and we put multi-signatures right next to them and squint our eyes, we can see that they're basically the same thing. At least they're very similar, okay? But the thing is that the construction of multi-signatures from batch arguments crucially relied on the somewhere extractability property. Now, why is that an issue? Well, first of all, we didn't even define somewhere extractability for monotone policy bargs. And I would argue that it's not even clear what the natural definition would be. So if the previous constructions actually relied on somewhere extractability, but we don't have somewhere extractability, then can we actually get any applications from monotone policy bargs? And our second result actually answers this question with yes. We can get applications without somewhere extractability. Namely, we show that we can use monotone policy bargs to construct monotone policy multi-signatures. The formal theorem statement says that assuming non-extractable monotone policy barg and something called a puncturable signature scheme, we can construct a monotone policy multi-signature scheme. So we trade off the somewhere extractability with this puncturable property of the signature scheme. All right, so with the time that I have left, I won't go through the entire construction, but I will at least look at the main building block that we use to get the monotone policy barg, and the starting point is actually going to be the previous work of Brakerski et al. So let's start with their main building block. They introduced something that they call a predicate extractable hash. And you can think of it as a generalization of SSB hash or some more extractable hash. So you have a hash key that you can program to bind on some things, but here you can program it to bind on multiple indices, not just one. So for example, you can program it to bind on Y1 being 0 and like the first bit being 0 and the 17th bit being 0 as well. And in addition, of course, we have a secret extraction trapdoor. So how would you use this thing? So you have this string that actually satisfies the binding constraints and you want to hash it. You do that, you get a digest. Now what you can do is apply the extraction algorithm with the secret trapdoor on this digest, and because this string actually matches the constraints, the extraction algorithm will be happy and will output matching. What happens if you hash a string that does not satisfy the constraints? So if we replace y by some y star that's actually 1 on the 17th bit, so again, it doesn't satisfy the constraint, then when we apply the extraction algorithm on the digest, it won't be happy, and furthermore, it will tell us, hey, this string is violating the constraints on the 17th bit. And they show that using this, this primitive predicate extractable hash, they can construct monotone policy bargs from bargs. And they show how to construct this thing from fully homomorphic encryption, and this is how you get their result. I'm oversimplifying, of course. You know, you have to actually do the construction and all that stuff. But the thing is, because of this strong extraction property, it seems like the FHE is actually inherent here, because you're doing this sort of like computation on the data without actually revealing what you're computing. So it feels like an FHE flavor thing. So how do we get around this? Well, what we do is we replace the predicate extractable hash, yeah, this circle, we replace the predicate extractable hash with something that we call a zero fixing hash. So it's very similar. Again, we can bind on some constraints, but what we have now is a relaxed notion of extraction. So our extraction algorithm only outputs a flag, either matching or not matching. So in the case where we're hashing here a string that is violating on some index, we don't output 17, instead we just output not matching. And because of this relaxed extraction property, we can actually implement this thing from a wider variety of assumptions. Namely, we show a generic construction using additively homomorphic encryption on bargs, and we also show a direct construction from pairings. Now, we have a weaker extraction property, so we work a bit like in a different way to move from here to actually constructing monotone policy bargs, but I won't have time to get into this. But this is like the main difference between the two constructions. So as a conclusion, we show here that additively homomorphic encryption suffices to compile bargs into monotone policy bargs. So this work actually requires additively homomorphic encryption over large groups. In a follow-up work, we show that any additively homomorphic encryption, for example, the Goldwasser-Micali encryption, which is just homomorphic with respect to bit XOR, suffices. All right, now on to open questions. So first of all, what are the minimal assumptions that we need to actually compile bargs into monotone policy bargs? So we saw that if we restrict ourselves to just log depth circuits, for example, then collision-resistant hash suffices. Here we tighten the gap a little bit from the previous work. We don't need fully homomorphic encryption, we just need additively homomorphic encryption, but can we bring that all the way down to collision-resistant hash? Another question is, do monotone policy bargs have additional applications, other than monotone policy multi-signatures? And finally, can we get monotone policy barg with a short CRS? So I didn't get into our reconstruction. I think someone else mentioned that question before. But we didn't get into the construction, but here our CRS grows with the size of the policy. So can we get something that's independent of the size of the policy? Again, the proof is short. I'm talking about the CRS. And that's it. Thank you.
Hi, can you give some intuition why you cannot get a general policy, like general circuit?
You mean from, can you hear me? Okay. You mean from collision-resistant hash?
No, like from bug to like a general policy bug?
Not just monotone policy. So think of a very simple policy that's not even batching. It just does a negation. Basically, if you can do that, then you give me a proof for a co-NP problem, right? So, and monotone policy bug, they just like make sense in the same way that when you're doing a secret sharing or aggregate signatures, you want to do something monotone. The more signatures you add, or the more statements that are true, the better. That's like from an application point of view.
I also have a question. So how does the size of the hash key in your zero fixing hash grow with the number of positions that you want the hash to be binding at?
It's polylogarithmic.
Oh, it's polylogarithmic.
Yeah, that's how we get succinct. Like we're gonna send the hash in our construction, and it has to be polylogarithmic. Otherwise, the proof is going to.
When you use the zero fixing hash in your construction, the number of positions that you want binding grow with the length. I mean, the number of instances that you want to batch.
Actually, we bind on the number of wires in the monotone policy, and that's so the CRS, the hash key there grows with the number of wires, and that's why the CRS is long. But the actual digest is polylogarithmic.
I see. Okay. Any other questions? Okay, let's thank the speaker then.